Pete, do we get our water in Arrowsic from an aquifer? And what makes our wells so different in yield one from another?
Paul, there's no aquifer, so to speak, water-bearing unit under Arrowsic. Our wells come from fractured bedrock, almost all of which is metamorphic and of different compositions and different compressibility or fracture competence. So mostly we have bedrock overlain by a very thin veneer of glacial deposits, almost none of which bear any relationship to our groundwater conditions. It rains, water seeps through the unsaturated zone to lower down to form a saturated zone, the top of which is called the water table. That's true no matter what the bedrock is like in areas with sedimentary rock aquifers or limestone aquifers or metamorphic rock. Another point is that the water table is configured much like the land topographic surface. Not precisely, but it's higher, slightly under hills, lower, and then the water table intersects major ponds or lakes and, of course, the river. So we're drilling wells in between those intersections, in between lakes, the river, and we're drilling down through a thin veneer of glacial deposits, if any. Mostly it's exposed bedrock. And we're drilling our wells into a variety of metamorphic rock. Metamorphic rock is, from the name, meta, changed, morph, form. So it's changed from its original composition or structure as sedimentary or igneous rock into metamorphic rock through high degrees of temperature and compression thousands of feet below the surface. Now it's exposed to us, and as it has been exposed through uplift and erosion of thousands of feet, the system tends to fracture. If you look at the bedrock map of the Bath Quadrangle, and we look at Arrowsic here, you see it's dominantly that yellow color. The yellow color is what I call sort of a garbage can mappable unit called the Cape Elizabeth Formation. It's a garbage can because it contains a variety of metamorphic rocks in it that were impossible to trace laterally and map out as separate units. So you've got this metamorphic rock unit that has a range in rock types or lithologies from here on the desk, from schist, which is very breakable, micaceous, mica-rich rock, to the other end of the metamorphic spectrum is a rock called pegmatite that's dominantly made of really coarse crystalline quartz and feldspar. If you were to look just at the samples of these, you might say, wow, this one is impermeable. In other words, how's any water going to get through that? And you look at this and say, maybe it would go through there more easily. It's quite the reverse. This rock, the pegmatite, fractures readily, and the fractures stay open to greater depths than what happens with the schist, the mica-rich metamorphic rock, that's so easily compressible, fractures don't stay open. The basic groundwater situation in Arrowsic is that it's fracture controlled. So where you've got a higher degree of open fractures interlaced, intersecting, you're going to get a greater yield from your well. And an example is if you stand doubling point area and go down toward the river, where I used to live over on Doubling Point. We were in a low area, and our well was underlain in bedrock, maybe not exactly by the same kind of mica-rich metamorphic rock, schist, but close to it. Whereas up on the hill, other wells dug deep into pegmatite had greater yields. They had greater yields because of the greater integrated fracture system found in pegmatite versus the compressible, non-fractured, non-open fractured bedrock called schist, very mica-rich. There are variations in the bedrock beyond these two. There's some intermediate fracturable quartz-rich metamorphic rock that would have an intermediate yield, but the two ends of the spectrum are the very mica-rich schist rock, such as what underlies the Kennebec, for example, and the more resistant, higher hill-forming pegmatite, but deeply fractured and integrated fracture system that gives you a greater yield out of your well. Disclaimer is I'm not a groundwater geologist.